For decades, chemistry teachers around the world told their students the same thing. Hydrogen is the most abundant element in the universe, but on Earth, it doesn't exist in free form. It's always locked up in compounds, water, hydrocarbons, never just hydrogen sitting there waiting to be used. I know this because I taught it myself. It turns out we were wrong, or at least significantly incomplete. Hydrogen does exist in free form on Earth underground, in sometimes remarkable concentrations, produced continuously by geology. In quantities we are only beginning to understand, and the implications for energy, for climate, and for the economics of entire industries are significant enough that the people whose job it is to find energy resources are now in a full-scale race to find it. This is the story of white hydrogen, and it starts, as the best stories do, with an accident and a lit cigarette. But to understand why that accident matters, we need a quick detour through hydrogen's slightly ridiculous color chart. Gray hydrogen is made by reforming natural gas, cheap but carbon-heavy. Green hydrogen is made by splitting water using renewable electricity, clean but currently expensive, around $5 per kilogram, and dependent on massive infrastructure. White hydrogen is different from all of them in one fundamental way: nobody makes it, the Earth does. It is 1987. A drilling crew in the village of Burakabagu in western Mali is boring into the earth looking for water. The Sahel is dry, wells are essential, and the crew has done this dozens of times. They don't find water. Instead, gas starts coming up the hole, odorless, colorless, invisible. One of the drillers leans over to investigate. He is smoking. The explosion that follows burns for weeks. Eventually, someone caps the well. The village moves on. The hole sits sealed in the ground for 25 years, forgotten. This was not the first time something like this had happened. It was just the first time anyone would eventually pay attention. As far back as 1888, Dmitri Mendeleev, the man who built the periodic table, recorded hydrogen seeping from a coal mine. Nobody followed up. In the 1920s, oil drillers in South Australia hit pockets of gas containing up to 80% pure hydrogen, capped the wells, and kept looking for oil. In the 1980s, geochemists in Canadian and Finnish mines found samples containing up to 30% hydrogen, scientifically surprising, since prevailing models said this shouldn't be possible. It remained a curiosity. For over a century, natural hydrogen kept announcing itself and being ignored. The industry wasn't looking for it. The frameworks didn't account for it. Back in Mali, in 2012, a businessman named Aliou Diallo hired specialists to re-examine the forgotten well. What they found was gas that was 98% pure hydrogen. Within a few years, that single well was running a 30-kilowatt generator, enough to power the village. A decade later, pressure in the well has not declined. If anything, it has increased. That last detail stopped scientists cold. It suggested something the prevailing models said shouldn't be true. The reservoir was refilling. It looks like the Earth has been making hydrogen for billions of years, through processes happening kilometers below the surface. The leading proposed mechanism is serpentinization. When water percolates deep enough to reach certain iron-rich rocks, a chemical reaction releases hydrogen continuously, as long as water and rock remain in contact. The honest answer is that we don't have the full picture yet. The Earth's crust is not a laboratory. What we know is that hydrogen is accumulating underground in concentrations that our models didn't predict. When data from the Malian field was published in 2018, the response was immediate. In 2022, French researchers looking for methane in the Lorraine Basin found hydrogen concentrations climbing from 1% at 600 meters to over 15% at 1,100 meters, suggesting a reserve of 46 million tons, potentially the largest natural hydrogen deposit ever identified. By the end of 2023, companies exploring for natural hydrogen had grown from 10 to 40, with active projects in the United States, Australia, Spain, Albania, and Colombia. A resource hiding in plain sight for over a century had become the most watched story in energy. The question now was whether it could actually deliver, and that, it turns out, is genuinely contested. The excitement is real, and the early data is promising, but the story is much less certain than most headlines suggest. The first issue is the trapping problem. Hydrogen is the smallest molecule that exists. It diffuses through rock and any material more readily than any other gas. For a reservoir to accumulate, you need a dense cap rock to trap the gas below it. In oil and gas, this is a solved problem. For hydrogen, the geological conditions that create reliable traps are not yet well mapped. The second issue is renewability. The Mali well suggests some deposits recharge as they're extracted, remarkable if true. But the French research agency, CNRS, argues that natural hydrogen production rates are globally far too slow to meet significant energy demand. The Earth makes hydrogen continuously, but not necessarily quickly enough. Third, scale. The USGS has modeled that there could be trillions of tons of natural hydrogen in the crust. What gets cited less often is the rest of the analysis, that most is likely too dispersed, too deep, or too poorly trapped to extract economically. The Hydrogen Science Coalition has stated that the odds of finding deposits comparable to major natural gas developments are relatively slim. The honest version of this story is not unlimited clean energy discovered underground. It's something more interesting and more uncertain, a resource that has existed for billions of years, that we only just learned to look for, whose true scale we don't yet know and whose discovery, even partial, could matter enormously. Set aside the geology and look at the numbers. Gray hydrogen costs roughly $2 per kilogram. Green hydrogen runs around $5 before infrastructure. Estimated extraction cost for white hydrogen, 50 cents to $1 per kilogram. If that holds at scale, a significant if, it doesn't just compete with other hydrogen. It makes them look like expensive workarounds to a problem geology may have already partly solved. Green hydrogen's investment thesis depends on scarcity, on the assumption that clean hydrogen must be manufactured. White hydrogen doesn't compete on efficiency. It eliminates the premise. Billions in electrolyzer infrastructure were justified on the basis that there was no cheaper path. If there is, those investment cases need to be rethought. Oil and gas companies may be the biggest short-term winners. Extracting white hydrogen uses essentially the same technology as natural gas: drilling, seismic surveying, reservoir management. The entire technical toolkit transfers directly. Companies with decades of geological expertise are extraordinarily well positioned, and some are already moving. The less obvious winners are developing nations with no fossil fuel reserves. For countries that have historically had no path to energy independence except expensive imports, white hydrogen changes the equation. Mali is the proof of concept. One well, no grid connection, a decade of stable power at near zero fuel cost. So where does that leave us? White hydrogen is real. We've measured it, burned it, and in one village in Mali, people have been living on it for a decade. It has three things going for it that are hard to ignore. Its carbon footprint at the source is minimal. Its extraction cost undercuts every alternative if the estimates hold. And it uses infrastructure and expertise the world already has. At the same time, the hype is running ahead of the data. We don't yet know how many Moly-scale fields exist, how reliably they recharge, or whether the geology that makes Burkinabe work is common or exceptional. Over the next decade, watch for the first long-running commercial projects outside Mali. Watch for whether geological maps of hydrogen-rich crust start appearing the way oil maps did in the 20th century. And watch whether real development capital, not just exploration budgets, starts moving in. The headlines will cool down, they always do, but the wells in Mali are still producing. And that, for now, is one of the most interesting data points in energy.